Hi and welcome to another lecture on Calculus 3. Today we are going to talk about curvature and the formulas for tangential and normal component of acceleration. Let's go ahead and take a look at this very fascinating topic. So we have some formulas we talked about in previous lectures. We practiced them and now today we want to see where they come from. The lecture today is going to be a little bit more involved than the previous one. It's intended for students who are headed toward mathematics, physics, or theoretical engineering. Let's go ahead and see what we had in mind last time. We talked about curvature. So we said the concept is very intuitive. If you have a curve, so suppose I have a curve here, and obviously I see that the curve is turning here. I want to define curvature. A practical thing to do is to choose 3 points and pass a circle through them. So now if we could do this thing for these 3 points becoming very close to each other, then the radius of this, so this has a radius, curvature is going to be reciprocal of this radius. Now doing this thing for 3 points very close to each other is a tough job. Last time we looked at some pictures to help us understand what's going on. Let me go ahead and take a look at this thing again. So in this red curve is an ellipse, and this circle is that circle I was talking about. This corner of this ellipse, we see it's turning rather sharply, and we get a small circle in that area. If we come to this point, we see that this thing is turning slowly, and in fact if I come close to that corner, the circle becomes much bigger, and since the curvature is the reciprocal of that, curvature becomes much smaller. So at this corner the curvature is close to a quarter, while when I go to this corner the curvature becomes close to 2. So we promised to go ahead and derive the formula for this thing. Let's see what is involved here. Let's remind ourselves what was the definition of it. The definition was rate of change of the vector of unit length that is tangential to the curve with respect to the arc length. So what does that mean? So suppose we have a curve, and then we go ahead and look at the unit tangent vector to this thing. So the unit tangent vector, we had called it t. So at the beginning, let's say this is t sub 1. We go a little bit further down this curve, and then I have another tangent, unit tangent. Let's call this thing t2. Well, from starting point to the ending point, we have traveled on some distance. Let's call that length delta s. What we are after is how much this unit tangent curve change while we traveled a length of delta s. So if I take t2 minus t1, find out the difference between these two, and divide this thing by delta s, I get a good approximation for the curvature. That's how the curvature is defined. That's the idea of the curvature. What we have in mind is to show that this definition leads to this formula. This formula is somewhat easier to apply than that one, but when you look at them, they don't look anything like each other. If you want to explain how does this lead to that, it's going to require a little bit of vector calculus. So whatever you learn about vectors in calculus 2 is going to be very handy here. And once we establish that, we are going to have the formula for breakdown of the acceleration to 2 components. If you are going on a curve, so again we are traveling on some curve, uh, we have a unit tangent vector again, let's call it t. We have a unit normal vector that is in this direction, we call this n. And then we could have an acceleration that's perhaps points in this direction or perhaps in this direction. So this is our acceleration. The question is, if I take this acceleration and break it into tangential and normal component, this one is called tangential component and this one is called the normal component. Tangential component turns out to be just the second derivative of arc length with respect to time. So that is essentially how fast your speed is changing. The other one is the normal component, the formula that's very famous in a variety of physics formulas. Sometimes you write it as v squared over r. Here we are writing it as a curvature times speed squared. We want to know where does this one come from. So as we said, a bit theoretical, but let's go ahead and get started. I'm gonna start with some preliminaries from calculus 2 and vector calculus. So we are going to refresh our mind about some basic vector facts. So if I have a vector, let's call it as A, and another vector B, the angle between two of them theta, you remember a basic formula that A dot B, dot product of these two vectors, turns out to be same as the length of A times the length of B times cosine of the angle between the two of them. This gives us, let's call this thing fact number 0. From this we get a very important formula, we use it all over the place, which is what's the projection of a vector on another vector. So suppose this is vector B and this is say vector A, and I take the vector A, drop a perpendicular to B, and I'm after this length. I'll call that projection of length of projection of A on B. What is that? So what we're trying to find out, what is X? Well, we are going to show that X has a very simple formula. It's A dot B divided by length of B. How so? Let's quickly show that. Suppose this is the angle theta. Then I see that X is the length of A times cosine of theta. X in fact is adjacent to this angle. So let's go ahead, multiply numerator and denominator of this thing with the length of B. So I take this thing as A cosine of theta multiplied by B and divide by the same thing. It doesn't change anything. Well, the numerator according to that observation is just A dot B and denominator is just the length of B. So that's a very basic so let's call it projection formula. This is a dot product. Basic fact about the dot product. This is the basic fact about projection. Now there is another projection you can do, which is the following. If I have same vector B and A, and I draw the normal to B in the same half plane where A is. So I look at this one. Now I find the projection of A on this normal. Let's call this thing Y. The question is, what is Y? The formula for Y is very simple. That's just A cross B divided by length of B. Again, why so? Quickly, let's do some basic trigonometry. Again, this is my angle theta. Y is the opposite to this thing, so Y is going to be the length of A times the sine of the opposite angle, sine of theta. What do you think I'm going to do now? Just the same thing I did over there. I write A uh, sine of theta times b over length of b. Now a sine theta times b, that's the length of the cross product of the two vectors a and b divided by length of b. So that shows that the length of the normal projection of a on b is going to have this magnitude. Next, we are going to go after some calculus problems. Calculus problem, suppose I have a vector a, I find the length of it, and then I want to take the derivative of the length. Derivative of the length. What we want to show, we have done this thing once before, but we're going to do it again. Derivative of the length is, in fact, projection of the derivative on the original vector. That the final formula turns out to be this. Derivative of the length of a vector is the derivative of a vector projected on the original vector itself. How do we see that? Again, this is going to be a repeat of something we have done before. First of all, what is the norm of a vector? Well, of course, that is dot product of it with itself raised to power of a half. Now suppose I want to take a derivative of this. So I take a derivative of the right hand side, a dot a to power of 1/2, and then we have to differentiate this. We just apply derivative rules. Derivative of this expression will be the exponent times derivative of the base, derivative of the first times the second, plus first times the derivative of the second, except times means dot product, times the original base to power of 1 less than the old exponent. So it will be 1/2 minus 1. Well, this is going to be 1/2. This is, of course, just 2 a dotted with a prime. These two are the same thing, so I'm doubling on that. 1 minus 1/2 minus 1 is minus 1/2, so I'll have I might write this thing, might as well write it in the denominator. Well, let's clean up. These twos cancel out. Numerator is a prime. Denominator, well, this is the length of a itself. This might look a little bit mysterious as to what happened. In fact, this is a formula that is very important and very useful in multivariable calculus as you apply to physics and engineering. It shows up in lots of places. So let me give a quick explanation for this thing, and we are going to move on. The formula is all that we need. If you have a vector, let's call this thing a, and then you change it by a small amount, so let's call this small amount delta a. Now you have a new vector which is a plus delta a. The question is, what is the change in the magnitude? That's what this derivative is referring to. What is the change in the magnitude of this vector? That is, if I have a plus delta a in magnitude minus a, what would that be? Well, what is that? Let's go ahead, try to figure this out by just drawing. I want to find the difference between these two sides. So I make a small circle out of this. This triangle, well, it's almost like a triangle. We might as well think about this side of it as a right perpendicular to this other vector. In this triangle, we are trying to find out what this is. That is the difference between the length of these two vectors. Well, how do we do that? If you look at this thing carefully, you'll see that what we are really doing is the projection of this vector delta A on that vector. Now that vector itself is close to the vector A, so the projection of delta A on that, or the yellow length, is going to be delta A dotted with A divided by A itself. So the formula that we have here is in fact an extension of this, but the one that we are going to use in our developments is going to be this one. Final item that I need to mention before we actually start with our main derivation is something named after Lagrange, one of the famous mathematicians. So we have so-called Lagrange identity. Sometimes it's referred to as the triple product identity. Triple product. Okay, this is also an identity that comes up in advanced math or physics, and it's the following. It's just about cross product of three vectors. If I have A cross with B cross with C, that is same as B times A dot C minus C times A dot B. Sometimes this is referred to as back minus cap formula. It's just a way of memorizing it. This is a formula that you can show by writing all the components and establishing that two sides are equal. It's going to be rather lengthy, rather tedious kind of a proof, so I'm going to leave that out of this discussion today. So we might make a use of this identity. Now let's go back to so these were our preliminaries, and what I need to do is to start from beginning and see how far we can go. So we want to show that the curvature that is defined as a rate of change of unit tangential vector with respect to arc length in absolute value, this thing is really same as acceleration crossed with the velocity divided by cube of velocity. How is that these two are the same thing? Okay, first let's remind ourselves what was t. T, unit tangential vector. So you have a curve, you have a tangent to it. Tangent is in direction of velocity. You make it unit length, and that's what your t is. So t is v over, v over the length of v. Now what we want to do is to find the derivative of this thing. So first of all, let's write dt ds, the item from which you have to take an absolute value. First we are going to change our differentiation variable to time. So I'm going to take this thing that's same as dt over d time over ds over d time. Okay, well, derivative with respect to time, we are going to adopt a notation of referring to it as t prime. Derivative of arc length with respect to time, so rate of change of distance over time, is just a speed. Speed is absolute value of velocity. Okay, so what do I need to do? I need to find t prime. So t prime, so t prime is gonna be v over v prime. Now we have to be careful with this. We have done it once before. Let's do it again. First, derivative of numerator. We are just applying the quotient rule. Derivative of the numerator times the denominator minus numerator as it is times the derivative of the denominator divided by denominator squared. So that's just a quotient rule. Now, who is v prime? Well, you remember we have the cast of characters: position, velocity, and acceleration. So this is position, this is the velocity, this is acceleration. So v prime, derivative of v is just a, and this is just speed, minus v prime. You might be wondering what are we going to do with all of these things. Derivative of absolute value of vector, that is what we derived over there, and now we are going to make use of it. So this is going to be v prime over v. Now we have to take this and divide it by absolute value of v squared. So let's take a common denominator. So I'll have a v times another v minus v, that is v prime, that was our acceleration. The v in the denominator and this v squared combine to get us v cubed. Okay, let's rewrite this thing one more way. V squared, I can write it as v dot v and v dot a, then I'll have v cubed here. So that's my t prime. What do I need to do with this thing? Well, here's what we need to do. I need to divide it by v and then take absolute value of it in either order. Let's go ahead and take the absolute value. First, I pay attention to the following: t prime. Next identity to use here is this Lagrange identity. I can write this the numerator that I have by comparing against this, that it will turn into a triple product. So I'll let you cross these two and notice that t prime is v cross a cross v divided by v cubed. Now next question is, well, what's the absolute value of this thing? Now pay attention to a small fact. We quickly get what the absolute value is. Let's go ahead for any two vectors a and v. Here, let's draw a picture, even though it doesn't have anything to do with this specific picture. Suppose this is v and this is the acceleration a. So a cross v, you remember a cross v from your calculus 2, this is a vector that's perpendicular to both of them and whose height is equal to length of a times length of b times sine of the angle between the two of them. Important thing is that this is going to be perpendicular to both of them, especially perpendicular to v. So if you want to cross v with this red vector, it's going to be the length of this times the length of that times sine of the angle between the two of them, and sine of 90 degrees is going to be 1. So that means when we want to find the length, this is going to be the length of v times the length of a cross v divided by cube of speed. Well, one of these cancels one of those, and I get a cross v over v squared. So we found out what is t prime. Now what do we do with that? We have to calculate t prime over v. So t prime over v, this is what we defined as curvature, or we derived that as a curvature. Well, I have to take this thing divide by another v, so I'll have a cross v over v cubed. So that's our first victory today. That's what we wanted to show, that the curvature that started as this definition has this alternate form, a cross v, acceleration cross velocity over cube of speed. That was our derivation. Now to the next observation. Let's go ahead. I'm going to rewrite, well, we want to show the following. We want to show that A has a tangential component and a normal component given by the following formulas. The tangential component is your linear acceleration, that is second derivative of distance to time. And then we want to show that an is your curvature times square of velocity. First of all, what is tangential acceleration? Well, what we have to do is consider the acceleration, consider a tangent vector. We might as well consider the velocity itself, and find a component of A on V. So that's going to be A dot V over V in absolute value. That is the component formula we learned way back here. Projection of a vector on another vector had this simple formula. Now we come to the derivation that we had. You remember we said d dt of v. Okay, what's the rate of change of? This is the speed. Rate of change, we just derived that here. Let's see if I can find it. Or let's just go up here. Here's rate of change of any absolute value of any vector is just that vector times rate of change of the vector divided by the length of the vector. So here, if I want to take the rate of change of this, I have to take the vector itself, take the derivative of that, and then find the projection of that over the original vector. So that's going to be times v over the length of v. So what are these things? This is a, this is v, and this is just the speed. So the tangential acceleration that we do by vector consideration, tangential component of a on the velocity, is same as the derivative of speed. Well, speed itself was derivative of distance with respect to time. So what we have here is that this becomes second derivative of displacement or excuse me, arc length with respect to time. Article number 2. If you want to find the normal component of a vector. Normal component, how did we say we do that? Normal component was so if I want to find the normal component of the A on the vector B, all I have to do is to do the cross product of A and B over the norm of B. So what we are going to do here, same way, it's going to be A cross with V divided by absolute value of V. Well, we just found a moment ago what A cross V is. A cross V is going to be K times V cubed. So I write this thing as K times V cubed, and this is just V. So it becomes K V squared. So we have shown the second component as well. The normal component of acceleration is equal to the curvature times the square of the speed. Okay, rather theoretical derivation, but again, this is the type of mathematics that's going to be awaiting you if you're going toward the advanced degrees in mathematics or physics or theoretical engineering. I hope you enjoyed it. Until next meeting, good luck and God bless.